Friends, welcome back. Today we will explore NMR Chapter 5, which deals aromatic rings currents, starting with the basics of benzene ring hydrogens. The ring current in benzene causes protons attached to the ring to appear in the range of 7 to 8 ppm. An anisotropy diagram will help us understand this effect better. Protons in a methyl or methylene group attached to the ring appear in the range of 2 to 2.5 ppm. Here, we see the ring current in benzene. The circulating pi electrons generate a secondary magnetic field that deshields aromatic protons. Next, we explore mono-substituted rings and the unique properties. In mono-substituted rings with an alkyl substituent, all ring hydrogens appear at the same place in the NMR spectrum. The ring current equalizes the electron density at all the carbons of the ring and, therefore, at all of the hydrogen atoms. This is the NMR spectrum of toluene, showcasing the distinct peaks for different hydrogen environments. Electronegative elements with unshared pairs shield the ortho and para ring positions, separating the hydrogens into two groups. Electron-donating groups shield these positions due to resonance. In anisole, the ring protons come at about 7.2 ppm. Notice the shielding effect on the NMR spectrum. When a carbonyl group is attached to the ring, the ortho and para protons are deshielded by the anisotropic field of the carbonyl group. This effect is sometimes seen with C-double bond C bonds as well. In acetophenone, the ring protons come at about 7.2 ppm, showing the deshielding effect of the carbonyl group. Now, let's look at para-disubstituted rings and the unique NMR patterns. 1. 4 disubstituted benzene rings will show a pair of doublets when the two groups on the ring are very different. An example is 1-iodo-4-methoxybenzene. This is the NMR spectrum of 1-iodo-4-methoxybenzene, illustrating the doublet pattern. Here, we see the NMR spectrum of 1-bromo-4-ethoxybenzene, another example of para-disubstitution. As the two groups in para-disubstituted rings become more similar, the NMR peaks move closer, and the pattern changes until all hydrogens are equivalent. This is the NMR spectrum of 1-amino-4-ethoxybenzene, showing the effect of similar substituents. Here, we see the NMR spectrum of paraxylene, or 1,4-dimethylbenzene, with its characteristic peaks. Finally, let's discuss hydroxyl and amino protons and the unique NMR characteristics. Hydroxyl and amino protons can appear almost anywhere in the spectrum due to hydrogen bonding. These absorptions are usually broader than other proton peaks. Carboxylic acid protons generally appear far downfield near 11 to 12 ppm. This is the NMR spectrum of ethanol, highlighting the peaks for hydroxyl and amino protons. In alcohols, the coupling between the OH hydrogen and adjacent carbon atoms is usually not seen. This is due to the rapid exchange of O hydrogens among various alcohol molecules in the solution. However, in ultra-pure alcohols, coupling can sometimes be observed. The exchange happens so quickly that the CH group sees many different hydrogens on the OH during the time the spectrum is being determined. Here, we see the NMR spectrum of 2-chloropropanoic acid. The spectrum shows distinct peaks, with the carboxyl group, COOH, appearing around 12 ppm. The other peaks correspond to the different hydrogen environments in the molecule. Now friends, let's discuss about the chemical shift reagents. These reagents interact with molecules and solvents, causing large changes in resonance positions of certain types of protons, such as hydroxyl, O, and amino, NH2. These changes can also be influenced by switching from usual NMR solvents to those like chloroform or benzene, which have local anisotropic effects. In some cases, solvent change allows partially overlapping multiplets to be resolved. Most chemical shift reagents are organic complexes of lanthanide elements. These complexes, when added to a compound, can shift resonances upfield or downfield. Elements like europium, erbium, and thulium shift resonances to the lower field, while cerium and samarium shift them to the higher field. Another advantage is that shifts similar to those at higher fields can be induced without needing an expensive higher field instrument. The shift change depends on the distance between the lanthanide element and the proton group, and the concentration of the shift reagent. Friends, I hope you like the series of NMR spectroscopy. Thanks for watching. Take care, goodbye.